Before we evaluate the limit of a piecewise function, I'm going to remind you of the definition of the absolute value function. And an absolute value of x is equal to x if x is greater than or equal to 0, and the opposite of x if x is less than 0. And so we'll use this definition to help us evaluate the limit of a fraction that has an absolute value in it. And so we'll also use the definition to rewrite this limit. It would be the limit as x approaches 0. We'll set this up as a piecewise function. And so for the part where x is greater than 0, the numerator would be x. So we're going to have x over x if x is greater than 0. And when x is less than 0, we're going to have the opposite of x over x. Now before we simplify this, I want to stress the point that notice that the equal sign is not included here as it is in the definition up here. It's because we're not just dealing with an absolute value function, we're dealing with a function that has x in the denominator. So you can't have x equal to 0 because that's not in the domain. So let's simplify this piecewise function. We get the limit as x approaches 0 of 1 if x is greater than 0, simplifying the x over x, and negative 1 if x is less than 0, simplifying the negative x over x. So when you want to evaluate a limit, remember that this is a two-sided limit, and in order for a two-sided limit to exist, the one-sided limits have to be equal. So we'll look at the limit as x approaches 0 from the left of the absolute value of x over x, and we'll look at the limit as x approaches 0 from the right of the absolute value of x over x. So at some point I'm going to graph this, but for now I want to use the function to help me evaluate these limits, the one-sided limits. So as x approaches 0 from the left, that means I want values that are less than 0 for x, and so I'm looking at the function that corresponds to x is less than 0, and that is negative 1. So the value of this limit is negative 1. The limit as x approaches 0 from the right, we're going to be looking at the function that belongs with the values of x that are greater than 0, and that is 1. So this equals 1. So since the one-sided limits are not equal, that means the limit as x approaches 0 of the absolute value of x over x does not exist. Let's take a second to show this graphically. I'll graph the piecewise function. For x is greater than 0, I'm going to have the constant function 1, and that is just a horizontal line to the right for x values that are to the right of 0. And to graph the second part of this function, it's equal to negative 1 if x is less than 0. So we've got this line right here. And so what really is here is an open circle because, and we put that in just to stress that x equals 0 is not in the domain of this function. And you can see here that as you approach 0 from the right, as your x values approach 0 from the right, your y values are approaching 1, which we got from the actual function. And as you approach, your x values approach 0 from the left, your y values are approaching negative 1. And so again, you can see here that the one-sided limits are not equal, so the two-sided limit does not exist. So at this point, I'd like you to pause the video and try the next few practice problems, and then start the video up to check your work. So use the strategies that we've learned in the last set of examples. Okay, student practice number 4, the limit as x approaches 9 of the square root of x minus 3 over x minus 3. We'll start by direct substitution. The square root of 9 minus 3 over 9 minus 9. We get 0 over 0. We know that we have to do more work. So we'll use some algebraic manipulation here. We have the limit as x approaches 9 of the square root of x minus 3 over x minus 9, we're going to multiply by the conjugate of the radical expression, numerator and denominator. We'll use the sum and difference formula for multiplying binomials, which would be the first term squared minus the last term squared. The square root of x squared is x, minus 3 squared, which is 9, all over x minus 9 times the square root of x plus 3. Don't forget your limit notation. I got caught again. Now the x minus 9s will cancel, so I have the limit as x approaches 9 of 1 over the square root of x plus 3. Now I can make my substitution and drop that limit notation. 1 over the square root of 9 plus 3 is equal to 1/6. Let's evaluate the limit from example 5 using the piecewise function. So 5a, we've got the limit as x approaches 1 from the left of f of x. So if we're approaching from the left, we're going to look at the function or the expression corresponding to values that are less than 1, which would be the negative 2x plus 4. So this would be the same thing as the limit as x approaches 1 from the left of negative 2x plus 4. This is a polynomial, so we just do direct substitution. Substituting 1 in for x, I get negative 2 times 1 plus 4, which is 2. So the left-hand limit, as we approach 1 from the left, is equal to 2. As we approach from the right, we want to choose values that are greater than 1. So we'll have the limit as x approaches 1 from the right of the square root of x minus 1, because this function corresponds to values of x that are greater than 1. Direct substitution, the square root of 1 minus 1 is equal to 0. So my one-sided limits existed, but because my one-sided limits are not equal, then the limit as x approaches 1, which is the two-sided limit, does not exist. The last problem just refers to the properties for limits, and so we're given 3 limit values. The limit as x approaches 7 of f of x equals 4, the limit as x approaches 7 of g of x equals 5, and the limit as x approaches 7 of h of x equals 8, and we want to evaluate the given limit here. So I don't need to write this out by putting all of the limits in. So 2 times the limit as x approaches 7 of f of x is equal to 4. So 2 times 4 minus g of x, so if I want the limit as x approaches 7 of g of x, which is 5, divided by the product, the limit of h of x, which is 8, times the square root of the limit of f of x, which is 4. Evaluating, you get 8 minus 5, which is 3, over 8 times the square root of 4, which would be 16. So the value of the limit is 3/16.